Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 7, 2026, about 2 days ago. It introduces PointWorld, a large pre-trained 3D world model that unifies state and action as 3D point flows, trained on a massive dataset of 2 million trajectories to enable zero-shot robotic manipulation. The paper is titled PointWorld, Scaling 3D World Models for In-the-Wild Robotic Manipulation. And as we'll see later, the results for real-world tasks like folding clothes and using tools are really impressive. Figure 1 illustrates the core concept behind PointWorld. In the center panel, we see how the model processes the world. Instead of relying on specific robot joint angles, it represents actions as 3D point flows, shown as purple arrows extending from the gripper. The model then predicts how the scene changes, generating flow vectors for the objects being manipulated. To support this, the left panel displays the massive diversity of training environments, while the right panel highlights the model's ability to generalize to real-world tasks like folding clothes or opening drawers without extra fine-tuning. So Figure 2 details the pipeline. Starting in the top left, the system takes an RGBD image and converts joint actions into robot flows, which represent the gripper's motion in 3D space. These robot points are merged with the scene point cloud in the top right. Then, the bottom left shows the architecture. It applies a frozen Dyno V3 encoder to the scene points and time embeddings to the robot points. This produces the output on the bottom right, a dense prediction of how the entire scene moves. Figure 7 charts the roadmap for scaling these world models, tracking how prediction error decreases with each architectural improvement. The top section shows that switching the backbone to Point Transformer V3 immediately outperforms older baselines like graph-based neural dynamics. Further down, integrating multi-layer features from Dyno V3 helps the model capture better visual details. Most importantly, the bottom bars demonstrate clear scaling laws, where increasing the model size from 50 million to 1 billion parameters drives the error down to its absolute minimum. Table 1 explicitly quantifies these trade-offs, comparing traditional backbones against the Point Transformer V3 series. The top section lists older architectures like PointNet and SparseConv, which serve as baselines. In contrast, the bottom rows track the new model scaling from 50 million up to 1 billion parameters. Remarkably, looking at the last row, even with nearly 1,000 times the parameter count, the latency remains around 120 milliseconds. This efficiency allows the model to achieve the lowest error rates on the far right without sacrificing real-time speed. So Figure 9 visualizes these scaling trends side by side. On the left, the data scaling chart shows that increasing the training set from 5% to 100% results in a steady, log-linear drop in prediction error. The right panel mirrors this for model capacity, tracking the gains as the network grows from 50 million to 1 billion parameters. Together, these plots indicate that the system has not yet saturated, implying that further scaling would continue to improve performance. Alright, having established the scaling laws, Table 2 assesses generalization capabilities across different environments. The table splits results into in-domain, cross-domain, and held-out real settings. Starting with the top row, the zero-shot results reveal that transferring between simulation and reality without adaptation yields higher errors. However, looking at the fine-tuned row below, we see that a short adaptation phase drastically reduces this gap. In fact, for the held-out real scenarios on the right, the pre-trained model matches the accuracy of a specialist trained from scratch. Wrapping up, PointWorld proves that representing robot actions as 3D geometry allows models to scale effectively across different embodiments. The clear scaling laws suggest that larger datasets will continue to improve physical reasoning, bringing us closer to general-purpose robots that handle complex tasks zero-shot. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.